Thank you very much, and thank you very much for inviting me to this symposium. And Al, thanks very much for doing a wonderful introduction to my presentation, because in effect we're going to be looking at the ore systems and setting in the Flin Flon Belt. I'm going to start with sort of a regional picture and then move my way in terms of scale down to the Lalor area, and then step back at the end just to take a look at what could be the possible scope for finding new mineralization in the Chisel Lalor Basin. So first of all, there's three things you need to know about the Flin Flon Greenstone Belt. The first is that the Flin Flon Belt volcanic rocks formed in a number of geodynamic settings, and this was determined using lithogeochemistry as a tool to identify all these different settings. So we have rocks that are formed in a juvenile oceanic arc environment, ocean floor environment, ocean plateau environment, ocean island environment, and then in a continental environment. So many, many different types of assemblages in the Flin Flon Belt. And I should point out the town of Flin Flon here and Snow Lake here, and this is basically what is considered to be the Flin Flon Belt. The second thing is that the Flin Flon Belt has a very long history. When I first began working in the Flin Flon Belt, it was thought that the volcanism in the belt occurred fairly rapidly over a short time of period, and then some of the rocks were eroded and formed these sediments to the north in the Kisinu domain to the north. We now know that the volcanic rocks in the Flin Flon Belt span a wide range in time. Most of them are formed in this age range here, about 1.88 to 1.9. And then there's a number of other volcanic rocks at the east end of the belt that occur in this environment as young as 1.83. And then there's a number of other different players in there. So this is a very complex system of volcanic rocks, not formed at one time, not formed in one environment. The third thing you know is that the VMS deposits in the Flin Flon Belt are selectively occur in oceanic volcanic rocks, and formed over a fairly narrow time span between 1.88 and 1.89 billion years ago. So it's these rocks here, the bright green rocks that we see all through the belt, are the main targets for VMS mineralization in this belt. You would not want to spend a lot of time looking for VMS deposits in the ocean floor assemblage here. So if you want to take something away from this, then is if you're going into a volcanic belt to search for VMS deposits, you have to understand that volcanic belts are not simple entities. They're very complex, and all of the rocks formed in many different geodynamic settings, and they formed at different times. And probably if you're looking in a volcanic belt, you're probably going to be restricted to a few assemblages that contain VMS deposits. And of course, in the Flin Flon Belt, that's these 1.9 to 1.88 billion-year-old oceanic volcanic arc assemblages. So these days, finding geophysical anomalies to drill, airborne geophysical anomalies anyways, it's relatively inexpensive to do this. But I would say that if you want to drill off these anomalies, you probably have to take into account the geology to have a cost-effective exploration program. In this section, we're going to take a look at how the Flin Flon Belt was assembled and why this is important. And to really understand this, we have to step back to what Al Galli was talking about, in that hydrothermal systems on the modern ocean floor, which is what you've got in the Flin Flon Belt, occur in a number of specific environments: mid-ocean ridge environment, over plumes, and in volcanic arcs. And these in yellow are all seafloor hydrothermal vents and related mineral deposits on the seafloor. And this is from a paper by Hannington et al., 2005. Second thing you have to understand is that the preservation of VMS deposits in these environments is quite different. For mid-ocean ridge and within plate VMS deposits, They're exposed on an ocean floor, and they travel across the ocean floor for several tens of million years before they are then subducted or consumed at the plate margins. Not a very good environment for preserving a VMS mineralization. Whoops. On the other hand, volcanic arc environments, the VMS deposits are rapidly covered, so they're better preserved. And because they're on the upper margin of the plate, they actually get accreted to other volcanic belts and to the volcanic arcs or to the continents. So they have a much better possibility of being preserved. In volcanic arcs, there's a number of different settings in which VMS deposits occur, and I'm only going to point out a few. They occur in a four-arc environment with a type of basalt that's very specific with bonanites. They occur in rifted arcs, failed rifts. This is the main environment for VMS mineralization, and they all also occur in back arc basin environments. And I would point out that all of these environments are present and identified in the Flin Flon Belt. Now, how do you recognize a volcanic arc setting if you're working in a volcanic belt? Well, arc basalts have a very distinctive chemistry as a result of their mode of formation, and I won't go into that. But they tend to have high thorium to niobium ratios, which is basically a subduction signature, and they have negative niobium, titanium, zirconium, yttrium, and hafnium relative to mid-ocean ridge basalts. So that's the way in which you're going to identify these guys that have a better potential for hosting VMS deposits. So let's take a look now at the Flin Flon Belt itself. It is an orogen that is identified as being a probable Wilson cycle orogen with opening of an ocean basin with Archean continents on the margin, and then gradual closure of the basin over quite a period of time. The closure of the basin began at between 1900 and 1880 million years ago with the formation of subduction zones and the formation of most of the VMS deposits that we find within certainly in the Flin Flon Belt. Continued closure went on until 1840 million years when final closure of the ocean basin took place, where the Archean cratons were impinging on the material in the ocean basin and thrusting these guys, the sediments, the volcanic rocks, even the plutons, up and out of the area between the Archean cratons. At a belt scale, this is what you see. This is a lithoprobe seismic section done from basically this point here over to west of Flin Flon. And you can see that at a crustal scale, you have shallow east dipping reflectors indicating the architecture of the belt, largely as a result of this final closure of the ocean basin. Corrigan, in a paper in 2007, suggested that the east end of the Flin Flon Belt, and that you should read for that, the Snow Lake area, may have developed separately from the main part of the Flin Flon, or central part of the Flin Flon Belt. And this little guy up here is a cartoon, a snapshot at between 1845 and 1840 million years ago, showing the development of the central part of the Flin Flon Belt as an arc-arc accretionary complex that's intruded by successor arc plutons. The Snow Lake area belt is considered to be developed somewhere out in this Manitoba Ocean, perhaps even marginal to the superior craton over in here. And it was not actually assembled with the central part of the Flin Flon Belt until final closure of this ocean basin at between 1840 and about 1800 million years ago. So here's a simple diagram of the Flin Flon Belt. Flin Flon here, Snow Lake here, your juvenile oceanic arc assemblages, your mid-ocean ridge, basalt back arc basin deposits in the mauve color, and over, I actually don't have them here, there's some continental deposits over in here. This is the Amis collage, in other words, the westerly part of the assembled basin that was formed by arc accretion between 1880 and 1870 million years ago. And these rocks are then intruded and stitched by these younger successor arc plutons, which range in age from 1870 through to about 1850 million years ago. So at about 1850 to 1840 million years ago, this was a microcontinent in the ocean basin. And the remainder, and then what happened was this thing shed sediments into the basin, forming the Kissinu deposits here. The yellow are turbidite sedimentary sequences. The blue units are continental and shallow marine sandstones. So the assembly of the eastern part of the Flin Flon Belt took place with basically southwest directed movement of the plate carrying all of these volcanic assemblages, and then assembly against the Amish collage, forming basically a fold and thrust belt against this microcontinent here. And there's large nap-like structures that were formed at this time. This is one up in the Batty Lake area in the Kissinu, what's called the Kissinu Belt. And then there's a very major antiform, the Anderson Bay antiform, that's present in the Snow Lake Arc assemblage, which we'll take a look at in a moment. And of course, northeast trending folds that cross-cut this, and I'm sure Meg is going to have a lot to say about these folds in her talk, which follows this one. Take a look now at the Snow Lake area, or the eastern part of the Flin Flon Belt. So that's the geology we're going to look at next. Eastern Flin Flon Belt, we're going to take a look at the components and the characteristics of the rocks in the eastern Flin Flon Belt. So here we are. This is the edge of the Amish collage, and you'll notice this Fourmile Island assemblage, and we're going to have a bit of a look at that in this talk because it contains some VMS mineralization, included the newly discovered and now mined Reed Lake deposit. But it also has all of the usual components that we see within the central part of the Flin Flon Belt. And that includes ocean floor basalts, that's these guys. Arc rift basalts, not very well represented, these guys up in here. And oceanic arc volcanic rocks, all of these pale buff, I don't know what you call it, dirty green rocks. And those are the 1.9 to 1.85 billion year old juvenile arc assemblages. And these are the guys that in the remainder of the belt contain VMS deposits. And all these little stars in here represent either significant VMS deposits and or mines. And you can see that the Snow Lake Arc assemblage over in here and the Fourmile Island assemblage over in here are the main places where VMS deposits occur in the eastern part of the belt. And the easiest way, I think, to take a look at the characteristics of the eastern part of the Flin Flon Belt is to take a look at this cartoon-like cross-section, which basically goes from the Fourmile Island assemblage and the newly discovered Reed Lake deposit across the Snow Lake assemblage where the Lalor deposit is and up north of the town of Snow Lake. And we have a series of different juvenile volcanic assemblages. Fourmile Island assemblage, Northeast Reed ocean floor assemblage, Snow Lake Arc assemblage, and the McLeod Birch assemblage. And this is probably a thrust repeat of this guy right in here. These assemblages are all have younger sedimentary panels in between them of 1.84 billion year old turbidites. So we have the volcanic rocks at approximately 1.89 billion years old, and the turbidites form 50 million years younger, interspersed basically in a thrust fold stack, in other words, a crustal stack, intruded by plutons that are about 1.83 billion years in age, saying that all of this occurred between formation of the turbidites at 1.84 and the emplacement of these plutons over a very short period of time. So basically, the eastern Flin Flon Belt is a tectonic collage, very different than the arc-arc accretionary complex that formed the Amish collage. What have I done here? Have I gone back? Yeah. So what we're going to do right now is take a look at three of these volcanic assemblages, the Fourmile Island assemblage, the Northeast Reed assemblage, and then start taking a look at the Snow Lake Arc assemblage, which contains the Lalor deposit. We'll start with the Fourmile Island assemblage. And this is formed predominantly of basalt. The basalts have back arc basin geochemistry. They're P2O5 rich, and they're strongly tholeiitic. And this would be the mafic volcanic environment that Al Galli referred to earlier. And in this environment, you get a lot of copper-rich deposits. They're very valuable because of high copper content, but so far they tend to be fairly small in tonnage. And they are spatially associated with rhyolite domes. And this is a geochemistry of the basalts at Reed Lake and these ones at Dickstone. They basically have a Morb type signature, a flat signature, except for this niobium low and thorium kick. And this is the subduction signature. So this is indicating that they're forming in a spreading environment, but with a subduction signature to these rocks. The northeast Reed assemblage over in here is composed almost entirely of basalt. There's no rhyolite at all, almost no volcanoclastic rocks, and also, despite fairly robust exploration in this area early in its history, early in the exploration history of the belt, no VMS deposits. The signature of these rocks is a little different. They have a Morb-type signature with depletion of heavy rare earth elements, and they have a very weak subduction signature. Compare that to the Fourmile Island assemblage. I know for geophysicists that this might not seem like a big difference, but it is quite a different sort of geochemical profile for these guys. The Snow Lake Arc assemblage is the real moneymaker so far in the eastern Flin Flon domain. There's over 44 million tons of VMS ore, either mined or in reserves in existing mines. The VMS mineralization here occurs in more than one environment, and that's what's interesting to me. The Snow Lake assemblage has 3 different geodynamic settings in it. The first of these is the Anderson sequence in this pale green color, and it is characterized by basalts which have a very depleted rare earth element content, thorium kick, and a niobium, negative niobium. Doesn't have a typical arc signature. These types of basalts, along with some of the other features in the Snow Lake area, suggest that they're probably formed in a nascent arc or in a 4-arc environment. Here's the Chisel sequence. And here's the Lalor deposit. It is part of in the Chisel sequence, and it's associated with all of the mineralization in the lower occurs at the contact between the lower Chisel and upper Chisel, and the rocks in the lower Chisel that are intimately associated with the mineralization have this very typical profile, very strong subduction signature, negative niobium, negative zirconium, negative hafnium, negative titanium, all features of subduction, and this is indicating strong fractionation, in other words, high-level intrusions that have fractionated quite a bit. The upper Chisel sequence up in here, that's this guy over in here, tends to have a more muted but very similar profile when the rocks are compared to mid-ocean ridge basalts. The last rock in this sequence is the Snow Creek sequence, and it has a flat profile, indicating it probably formed by extension, probably as an extension of the greenstone belt here, of the volcanic arc assemblage, the Snow Lake one. Now, we have 2 main VMS environments. The one down in the Anderson sequence, all copper-rich deposits. The sequence that we're interested in here is the Chisel sequence. And all of the deposits in the Chisel sequence occur at this contact between the lower Chisel and the upper Chisel. These are several of the deposits in the area, and they're all zinc-rich. So diagrammatically, if we look at this, this is the Anderson sequence. That's this guy up in here. These are the low titanium basalts, large trondhjemite pluton in here. And this one has a strike length. You can see it's more or less conformal. It has a strike length of about 25 kilometers. And the VMS deposits in this environment are associated with rhyolites that can be demonstrated to be derived from this subvolcanic intrusion, and are associated with a very high temperature, broad alteration system that's several kilometers long and kilometers wide. This is a high temperature alteration zone, and these are disconformable alteration pipes leading up to the VMS deposits. A classic bimodal mafic felsic environment, very typical of the Noranda sequence, except it's a different geochemical setting. The Welsh Lake basalts continue, and at the top of the sequence there's a huge zone of silicification and felspithization and a barren sulfide horizon at the top of that. The mature arc volcanic deposits are located at the top of the lower Chisel sequence, and they're basically related to extrusion of geochemically involved magmas. That's what I showed you before. And they're spatially associated with phases of the Richard Lake tonalite, with dacite dikes, with dikes that feed the Moor basalt. And it can be clearly shown that the alteration is spatially associated with and occurred at the same time as the extrusive volcanism. The photolake deposit occurs in the upper Chisel sequence. The exact place of it in this setting is not very well understood. And Meg Engelbert, who's talking next, may have something to say about that. And of course, as Al said, the next thing that happens to these VMS systems is they're involved in deformation and orogeny. Here, this is the final closure of the Trans-Hudson Ocean, or the Manitoba Ocean, with thrusting, folding, and placement of this late Gabbro intrusion. We haven't been able to date it yet, so that's not very well proven. And then an episode of regional metamorphism that's modified all of the altered rocks in the footwall to these deposits. We'll take a little closer look now at the lower Chisel sequence and its boundary with the upper Chisel sequence. And again, this is the money maker here, this horizon in here, at the contact between the lower and upper Chisel. So this is a diagram of these suites of rocks. The lower Chisel has a suite of rocks in the lower down the sequence that are largely volcaniclastic, and I won't go into them too much. The sequence that seems to be associated spatially with the mineralization is this Moor basalt, powderhouse dacite, Chisel sequence. All of these guys are highly fractionated and have lanthanum-ytterbium ratios greater than 10. They have a number of other features that are high uranium, high thorium, high zirconium. So it's a whole plethora of elements that identify these rocks. They also have the same chemistry as the big synvolcanic plutons that underlie this area. So here's the dacite dike complex that feeds the powderhouse dacite, and the Richard Lake tonalite, of which Al believes this dacite dike is the first phase of this particular intrusive event. Now, one of the things that's really fascinating here is the Chisel Lalor alteration system, and we're looking again now at an ore system. And so we're going to go through this quickly. It's such a good example of an ore system that I thought it was worth presenting. The rocks in different colors in here represent different things. This zone of blue rocks are rocks that have been silicified and felspithized. In green are rocks that contain coarse amphibole porphyroblasts, and we really don't understand what the chemistry of this is. And then we have a broad sub-concordant alteration zone characterized by quartz garnet metamorphic mineral facies, and then these upflow zones, discordant upflow zones, which are characterized by garnet, storolite, cordierite, and thopholite, kyanite. So if we take a look at this system, it adheres to the classic model in that we have the heat source. That's the Richard Lake Pluton, the dacite dike complex. We perhaps have the downflow zone here, the recharge zone, in these amphibole porphyroblastic units. Now in this system, a reservoir cap is thought to be formed by these downflowing fluids, which are sealing the system, sealing the porosity, and causing a high temperature reaction zone to occur between the heat source and this reservoir cap. And that's these sequence of rocks in here. They're silica, feldspar-rich rocks, and we haven't done much work on it, but they are depleted in some of the metals that are occurring higher in the VMS deposits. The breach of the reservoir cap allows these high-temperature metalliferous fluids to move to the surface, where they undergo a lot of physiochemical changes and deposition of the base metal sulfide deposits. The third element to this deposit is this large zone of subconcordant alteration, which has a very large footprint. It's well over 9 kilometers in width and over 2 kilometers in, strike length, over 9 kilometers in strike length and 2 kilometers in width. And this is probably as a result of high porosity of all of the rocks that are hosting this VMS forming system. So let's take a very quick look at this system. These are myrolitic cavities in the Richard Lake intrusive complex. And Al Galli did a study on all of the synvolcanic intrusions in the Snow Lake area and published a paper in 2003 which discusses all of the features in these intrusions that show they're very high-level intrusions. This is basically a gas cavity, quartz rim on it, and epidote filling the cavity. As Al mentioned, for the picture he showed of the polygonally jointed Sneath Lake Pluton, the Richard Lake intrusive complex shows the same thing. So what this is saying is that the crystallization of the Pluton took place, it got fractured, and then the geothermal system basically collapsed back into the Pluton and then altered it, probably post-dating the formation of the VMS system. So it's the last gasp of the VMS system. But identifying these kinds of features within within a tonalite Pluton takes you into the right area. Here are some of the synvolcanic dikes. This is a flow-banded dacite dike cutting across Edwards Lake mafic tuff. I'll show you some examples where there's silicification marginal to these dikes. You don't see it too much here. This is a feeder for a synvolcanic dike feeder for the Moore Lake basalt. And in fact, there's actually been 2 intrusions along this. You can see the original intrusion here with highly amoeboid margins, and then a later intrusion, which also have some amoeboid margins on them as well. So this is an extensional feature opening up with the mafic magmas being placed into it. In this environment, you see a lot of epidote and quartz silica, altered rocks marginal to these synvolcanic dikes. And in fact, in the outcrop, you can follow away from these synvolcanic dikes for about 5 meters, and you'll see evidence of silicification and epidotization, showing that they're clearly part of the alteration system, as well as being feeders for the overlying flows. Here's another nice example of this. This is actually I'll start with this one. This is the Moore Lake mafic dike on very small scale. There's the dike margin. This is pervasive silicification adjacent to the dike, mottled silicification that's taking place adjacent to the pervasive silicification, and then sort of a nebulous bleached zone out here. This is the bedding in the mafic wackies, and here's the cross-cutting mafic dike that's a feeder for Moore basalts. This is an example of some of the alteration that takes place in the coarse volcanoclastics. This is a silicified felspithized margin on a large clast. It actually has these mottled or egg-type alteration structures in it, and also in the matrix between the bigger fragments. So this is all occurring in this zone of silicification. Then I'll be fine. Now, not always is that silicification, felspithization pervasive. In some cases, it's localized along fractures. Here's an example within a relatively unaltered Edwards Lake mafic breccia, this guy, with the alteration along these fractures. Here's another good example here. Here's mottled silicification, where you get this very, pressing the wrong buttons here, where you're getting a mottled silicification. This is a kind of a strange beast. I'm sure if you ran across it in the field, you'd kind of wonder what the heck it is. This is a zone of quartz feldspar alteration that's discordant to the bedding. This is the bedding in the Edwards mafic tuff, and you can actually see very delicate bedding lode structures in here, lode and right there with flames. So these are relatively pristine-looking rocks generally, but when they get altered, they go to things like this and this, which are almost unrecognizable as still being part of this Edwards Lake formation. Here's an example of the overprinting iron and magnesium alteration. It's overprinted a lot of the matrix in here. It's garnet rich, but you can see just faintly in here little fractures that are cutting across the outcrop. These are garnet, chlorite, biotite, storolite filled or mineral assemblages indicating iron magnesium alteration zones, probably an upflow zone in this alteration complex. Here's an example of silicified fragments with an iron magnesium altered ground mass formed of garnet and chlorite. This is a dacite dike, one of the dacite dikes that feeds the powder house dacite, which is right below the mineralization. And you can see that it's highly altered with all this pink material in here being garnetiferous. One of the things that was found during the mapping that Al Galley and I did was an area that had a lot of granite, and it was up on the west side of the Chisel Lake gabbro, which is a late pluton. And it was indicating that we're dealing with a system that probably was a mineralizing system. Granite is very prominent in the footwall to the Lalor deposit. This guy here is over on the other side of a gabbro pluton from the Lalor deposit. Here's an example of an iron magnesium alteration, now containing storolite, garnet, biotite, and these are silicified Moore basalt breccias. This is the bedding direction, and this is the metasomatic front. Here are dacite dikes. These synvolcanic faults often are intruded by dacite dikes, feeders for the volcanism, and mafic dikes, feeders for the Moore Lake, often themselves altered. These are garnetiferous zones on the overprinting the dikes. Get into the ore deposit itself. This is a characteristic feature of all of the deposits, Chisel, North Chisel, and Lalor. These ones are specifically from Lalor. Large kyanite porphyroblasts, and these are basically representing a complete destruction of feldspars and the remaining rock being silica and aluminum rich, and of course forming kyanite. Here's large storolite porphyroblasts in this footwall system, and lots of granite. And these are the things that were seen when the drilling took place on the North Chisel deposit. All three deposits, Chisel, Lalor, North Chisel, have a carbonate-rich alteration, and it's often expressed as tremolite chlorite-rich rocks, mottled carbonate, and many of these rocks contain little veinlets of chalcopyrite galena or spotty galena, and many of these particular zones contain elevated gold values. Take a look now at the lower to upper Chisel contact. And this is the contact, and it's important, of course, because this is the place where all of the VMS deposits occur in the Snow Lake area. And there are some features of it that are a bit unusual, and I'll go into that and discuss what some of the possibilities could be. So different rocks overlie and underlie that contact. So here's this on a geological map. So you can see just by the different units that are coming across that contact that there's a lot of different rock types at that contact, both above and below. And as a matter of fact, when you get over to the Anderson Lake deposit, which is part of the Welch Lake basalt down in here, within a distance of about 200 meters, you go from the Anderson deposit up into the mafic tuff breccia of the Three House Formation. That's this blue guy right here. So something funny is going on. We'll take a look now at the geological map of the Chisel Lalor area and the Chisel Basin. This would be considered the Chisel Basin up in here. And we'll take a look at some cross sections that are important in understanding what's going on. This is a cross section that was put together by Al Galley and Jerry Kitzler very early in sort of the geological work that was done in the Snow Lake area. And it shows the Chisel mine mineralization here, right at the contact between Lower Chisel and the Three House Formation. But if you follow up the Three House Formation, which does this, At this point in time, you have a completely different suite of rocks up in here. So south and north of the Chisel Basin syncline, you have a different stratigraphy. And also the mineralization does not tend to follow that contact. And this was something that Al Galley and Jerry Kitzler recognized early on. So here's the Chisel mineralization, North Chisel mineralization, and some mineralization way out in here. So the mineralization seems to be dipping off to the northeast, whereas the upper Chisel sequence are actually being folded up. So what does this mean? Lateral facies, variations in the upper Chisel sequence, possibly a caldera, possibly a synvolcanic fault. And I know that this was an early idea, and it's being followed up now by Harold Gibson and his students, and I think they kind of like this idea. The other possibility is that there's actually an erosional unconformity at the base of the upper Chisel sequence, and I think this one is not so widely considered with favor. And the one that I kind of like, which I'm having more trouble justifying, is that the contact is a thrust fault. So here would be the thrust fault coming across in here. And I put this warning. This is kind of warning you'd get on a cigarette package that says, you know, smoking these guys will be detrimental to your health. Well, perhaps buying into this idea of the thrust fault along this contact might be detrimental to your geological interpretations. But for the next while, I'm kind of addicted to this thing, and I'm going to stay with it for a while. So again, these are some other north-south cross sections. This one is from Ghost Lake deposit up through here to Photo Lake, and this is the hypothetical fault in here with the rocks underlying it being the calc-alkaline fractionated sequence with high lanthanum neoterbium, mainly altered, and then the rocks above, which are upper Chisel, low lanthanum neoterbium, and not very altered. And you'll notice here that the Photo Lake VMS deposit occurs actually in this ghost Photo Lake rhyolite, perhaps in an upper thrust panel. And there is some evidence for this thrust, which is this guy that comes down here, this fault feature that comes down in here. This is a cross-section from surface to depth of the Lalor deposit. This is the cross-section over here on 5350. And here we see the rocks in the hanging wall. And one of the things that struck me when I first logged some of the holes was you would follow these holes almost down to the mineralization going through the units that are present at surface. And one of the things I proposed was, again, this might be this hanging wall thrust fault. Rocks above the thrust fault, or hypothetical, whatever you want to call it, are not altered. They have normal sort of chemistry. The rocks below it have this elevated lanthanum neoterbium, often greater than 15, and they have lots of alteration associated with them. These are some alteration indices on this section showing that here's the mineralization, there's the number 10 lens. These are sort of the lower footwall lenses, and you can see on the basis of the Hashimoto index that the alteration gets much more robust as you go towards the north. And this has some implications in terms of the environment for the mineralization up over in here. I'll do another mine geology really quickly. Actually, I think I'm going to leave this for Craig, so we'll go through that pretty quickly. And we'll take a look now at the 2007 seismic image of the Chisel Basin. Now, first of all, we'll take a look at some of the deep drill holes that were made in the Chisel Basin. This is on the Lalor mine. The drill holes were hitting altered rocks and mineralization at around 600 meters below surface. This is a drill hole on a DPM anomaly just north of Chisel Lake. It hit very altered rocks at 702 meters. This is the discovery hole for the Lalor deposit, Dub 168. It hit altered rocks and mineralization at 782 meters. This is a hole that was drilled in the basin. It was kind of a hole that Jerry Kitzler put out in the basin because he thought there was real potential out in the basin because he noticed all of these altered rocks and he felt you might be able to hit them at depth. And he drilled a hole which intersected alteration at 1,146 meters and minor chalcopyrite mineralization. and these are two other deep holes. Look at where the alteration begins. So you get the idea that perhaps underlying this whole basin is a northeast dipping zone of highly altered rocks. In 2007, this is a seismic reflection survey that was done, and we can see plotted on this very crudely, I must say, the Chisel deposit, Chisel North deposit, and you can see the north dipping reflectors that are going basically up the highway past the Photo Lake deposit and north of it. These are some of the drill holes. These are some of the geology on the drill holes. This is Al Galley, Jerry Kitzler's profile here. This is Alteration, hit in Dub 166. And this was, at the time, a suggestion. This is perhaps the Chisel Lalor horizon and or fault. This is one of the cross sections I more recently put together, and it tends to show that it's off the section, so it's hard to relate it to this section exactly, but it does show this structure tending towards here. It might be maybe up in here. So in fact, the fault or disconformity, whatever you want to call it, is higher in this sequence. And I would point out right here, if you look here, look at this nice little seismic reflector in here. And this is the thrust fault that's portrayed. So that it's perhaps picking up that thrust fault. So I'll come here to the Don Sangster. And what Don Sangster said in 1980, he said it earlier in 1972, but he also published it as a paper in 1980. And what he said was the Snow Lake area is underexplored. For the size of it, for the number of plutons that are available, it's underexplored. Only small deposits were found. So I guess what I'm going to put to you is that now that we found the Lalor deposit, have we explored this area, or is there more potential in it? And I would say on the basis of the extent of the alteration that we see in the rocks at